guys, welcome back to my YouTube channel. Today I am going to solve day 30 problem of this month on Leetcode. Before starting, if you guys haven't subscribed my YouTube channel yet, then please go ahead and subscribe it. Now without any delay, let's get started with today's problem. So today I am going to solve problem number 1579. Remove max number of edges to keep graph fully traversable. Okay, so in this problem we have two persons named Alice and Bob, and they have an undirected graph of n nodes and three type of edges. Okay, so what are the three types of edges are there? So one is type 1. Okay, and the type 1 is an edge that can be traversed by Alice only. Okay, so here see this type 1 is indicated by a red color. Okay, type 2 is a edge that can be traversed by Bob only. Okay, and it is indicated by a green color. Okay, and type 3 is a edge that can be traversed by both Alice and Bob, and it is indicated using this blue color. Okay, so we have given an array edges. Okay, where edges of I is equal to type. Okay, so first this type is given to us. Okay, if it is type 1, that simply means that Alice only can traverse that particular edge. If type is 2, that simply means that only Bob can traverse that particular edge. If type is 3, that simply means that both Alice and Bob can traverse that particular edge. Okay, and UV, okay, it represents a bidirectional edge of type between nodes U and V. Okay, we have to find the maximum number of edges you can remove, so that after removing the edges, the graph can still be fully traversed by both Alice and Bob. Okay, the graph is fully traversed by Alice and Bob if starting from any node they can reach all other nodes. Okay, and in the end we have to return the maximum number of edges you can remove. Okay, or we have to simply return -1 if Alice and Bob cannot fully traverse the graph. Okay, so this is a hard level problem, and this question is very important, and this question is asked by Google and many other big companies. Okay, so now let's understand this problem with an example. Okay, so see this example one. Okay, so n is equal to 4 means total 4 number of nodes are there, right? 1, 2, 3 and 4. Okay, and these are the edges. Okay, so here this first value is nothing but it is showing the type. Okay, and this value is showing nothing but U starting point, and this V this value is V, that simply means the ending point. Okay, so here see first type 1 is for Alice, right? Type 1 is for Alice and it is indicated by red color. Okay, so here see where type 1 is there. Type 1 is here, type 1 is here, type 1 is here. Okay, so let's match let's first name the nodes. Okay, so let's name it like this. This is 1, this is 2, okay, and this is 3, this is 4. Okay, so now red color na for Alice, red color, right? For Alice, red color. So 1 to 3. Okay, let's match let's create one edge. 2 to 4, so let's create one edge, and then 1 to 2. Okay, so this is for Alice. Okay, now let's move to the Bob, and for Bob this color is green, right? So for Bob here this edge is there, right? Type 2. So 3 to 4, so let's match 3 to 4. Okay, this is for Bob, and type 3 is for both Bob and for Alice, right? And it is indicated using blue color, right? So 3 is here and 3 is here. So 1 to 2 there is one edge. Okay, so let's create one edge 1 to 2, and 2 to 3 there is one edge. Okay, so let's create one edge 2 to 3. Okay, this is done, right? So this is how this graph looks like, right? So now if we can just remove the two edges, right, that is this 1, 1, 2. Okay, if we remove this edge, okay, and if we remove this edge 1, 1, 2, 3, okay, then we can also traverse the graph fully, okay, by both Alice and Bob. Okay, the graph will still be fully traversable by Alice and Bob. Okay, if we just remove these two edges. Okay, so let's try to remove these two edges. Okay, so 1 is for nothing but Alice, right? 1 is for Alice. Okay, that simply means red color pencil. Okay, so let's remove the red color pencil from 1 to 3. Okay, 1 to 3, let's remove this. Done. 1 to 1, 1 for allies, and 1 to 2, 1 to 2, and that simply means red color. So let's remove this one. Okay, this is done. Now see, let's say allies start from this position. Okay, let's say allies start from this position. Okay, so this is blue color pencil. Okay, both allies and Bob can go. Okay, so allies reaches here. Then this is a blue color pencil. Okay, allies reaches here. Okay, then again allies goes back, allies again reaches here, and then here allies can go now from 2 to 4. Okay, there is a red color pencil. Okay, allies reaches here. So allies fully traverse all the 4 nodes. Okay, this is for allies. Now let's see for Bob. For Bob, a green color pencil. Okay, so let's say my this person Bob start from this position. Okay, 1 to 2 he can go, because blue color simply means that both allies and Bob can traverse. Okay, so Bob reaches here. Then 2 to 4 Bob can go, because this is a red color pencil. So but from 2 to 3 Bob can go, because this is blue color pencil, and both Bob and allies can traverse. Okay, so Bob reaches here. Now from 3 to 4 Bob can go, because this is a green color pencil, right? So Bob can go here. So Bob also traverses this complete graph. Okay, so how many edges we have removed? We have just removed these 2 edges, right? So total number of edges here, the total number of edges are 6, and we have removed 2 edges, right? So how many edges are there right now? 4 edges right now, right? Using just for these 4 edges, we can completely traverse this whole graph for both allies and Bob. Okay, so 6 minus 4 is nothing but 2. Okay, since we have just removed 2 edges now, so our output is going to be 2. Okay, so removing any additional edge will not make it so the maximum number of edges we can remove is 2, and 2 is our output. Okay, so I hope that you guys are clear, okay, with this. Okay, so now how I am going to solve this problem? Okay, so I am going to solve this problem using DSU. Okay, what is DSU? So DSU is nothing but Disjoint Set Union. Okay, and we also call it as a union find data structure. Okay, so let's read about this DSU. Okay, so DSU, also known as union find, is a data structure that keeps track of a set of elements partitioned into a number of disjoint non-overlapping subsets. Okay, it is useful for handling dynamic connectivity queries, such as determining whether 2 elements are in same subset and efficiently merging subsets together. Okay, so what are the key operations for this DSU? Key operations are find and union. Okay, so what is find? So it is determine whether subset a particular element is in. Okay, it is going to determine which subset a particular element is in, and this can be used to check if 2 elements are in same subset. Okay, find operation. And union operation is used to join 2 subsets into a single subset. Okay, and there are some optimizations that we do on this DSU, and these 2 type of optimizations are path compression and union by rank. Okay, so path compression, this optimization is used for used with the find operation, and union by rank, this optimization is used with the union operation. Okay, so what are some key applications, okay, where we use this DSU? Okay, so in Kruskal's algorithm, we are going to use for finding the minimum spanning tree of a graph. In connected components, okay, in a graph to find all the connected components. In cycle detection, we can use in an undirected graph. Okay, so this is a path compression. So let's say there is one subset, okay, from 0 to 1. Okay, so it can be represented as below. Okay, so see here, 9 and child of 9 is 4. Okay, so here 0 is connected with this 4, 3 is connected with 0. Okay, so if we just apply this find for this element 3, okay, so when find is called for this 3, okay, we traverse up and find 9 is the representative of this subset. Okay, so this 9 is the ancestor, okay, the topmost level. Okay, so with path compression, we can also make 3 and 0 as the child of 9. Okay, so directly see here, 0 and 3 we make as the child of 9 directly here. Okay, so this is nothing but path compression. Okay, so instead of finding like this 3 to 0, then 0 to 4, then 9, okay, so we can just directly make that as my child. Okay, that as the child of this 9. Okay, 0 and 3. Okay, this is for path compression. And union is nothing but, let's say there are these single element subsets, okay, 0 1 2 3. So if you do the union between u1 0 and 1 initially, so you make the 1 as a parent of u. Okay, here, then after that, if you want to make the union of 1 and 2, okay, so in that case you are just going to use that parent which has most number of children, okay, initially. So here see, this is already one tree now, this is already one tree, okay, and this one is already one parent, okay. So if you are doing the union between 1 and 2, then you are directly going to use this as parent, okay, this one as parent instead of 2, okay. So here see 1 and 0, okay, this is one tree, right? And if you do the union of 1 and 2, then instead of making 2 as the parent of 1, okay, so this tree will have higher length, okay. So we are going to keep our tree as small as possible, okay. So see here, length is going to be increased, okay. So here we are just going to make this one as the parent, okay, because this has higher rank, okay. So we are just going to increase the rank of parent whenever we are doing the union, okay. So we did the union of 1 and 0, then we make this 1 as parent now, so we are going to increase the rank of 1, okay. So here rank of 1, let's say 1, and initially rank of all the elements are 0 now, 0 0 0 0, okay. So if we do the union of 0 and 1, so for this parent I am going to increase the rank, okay. Then whose value has higher rank, I am going to make that as parent, okay. So here when I do the union of 1 and 2, again I am going to increase the this rank for 1, okay. So 1 rank is 2. Now when I am going to do the union for 2 and 3, so both have the same rank, okay, 2 0 and 0, okay. So here I am just going to make 1, okay, 1 as the my parent, okay, because 1 has the higher rank, okay. Okay, so we have to do these two operations, okay. If you don't know these two things, then just comment in my video, okay, I will explain in detail, okay. But right now let's move to the this specific problem, okay. So this is my example one, okay. So why I am going to use DSU, okay. So first question is why I am going to use DSU, okay. So see, in the brute force algorithm, what you are guys are going to think, you are going to remove one edge, okay, and then you are trying to find whether we can go, whether allies can go from 1 to 2, and whether both can go from 1 to 2, okay. If it is possible, then it's good to remove the edge, okay. If it is not possible, then you are going to maintain that edge, okay. So definitely this is going to take a lot of time, okay, and definitely we will get errors with such a code, okay. We will get time limit exceed error or something, okay, or whether solution is not possible using this, okay. So definitely I'm not going to use BFS and DFS for this problem, okay. So now initially what I'm going to do, I'm going to treat all these nodes, initially all these nodes 1 2 3 4, okay, all these nodes as the individual components, okay, as the individual components, okay. I'm going to treat them as individual components. Then after that I'm going to and then after this I'm going to make the path between them, okay. Initially I'm going to treat them as separate, okay. So that simply means DSU, okay. Initially I'm starting from separate nodes, okay. Everything is separate, okay. So see here, is a data structure that keep track of a set of elements partitioned into a number of disjoint non-overlapping subsets, okay. So initially I'm going to treat them as like this, okay. So see here, okay, before moving further, here see, one, okay, this is node 1 and this is node 2, okay. Okay, so here type 1 is for allies, okay. So here I make the path for type 1, okay, type 1, and type 2 is the path for green, okay, Bob, okay. So this is for type 2, okay. Now see here, type 3 is for both allies and Bob, okay. So type 3 is blue now, so here I am writing type 3, okay. This is T3, okay. So here if T3 is possible, then why I am writing T1 and T2, okay. What is the use of writing T1 and T2, okay. We have to keep the minimum paths, na, right? We have to keep the minimum paths, right? So why we need one extra edge here, okay. So if T3 is there, then directly use that, na, because T3 is used by both T1 and T2. T3 is used by both allies and Bob, okay. So definitely I'm going to give the priority to this T3, okay. So I am going to give the priority to type 3, okay. So that is why I have sorted the edges like this, okay. So first type 3 is coming, okay, then type 2 is coming, and then type 1 is coming, okay. So I hope that this line is clear, right? Now here n is equal to 4, okay. So I'm going to, okay, so here see, this graph is mixed for both allies and Bob now. So I'm going to create a separate graphs for both of them, okay. So I'm going to create one class, and in that, after creating that class, I'm going to use two objects, okay. So one is for allies and one is for Bob, okay. So let's say here components like this, okay. So let's say initially there are four components, 4 components for Alice and 4 components for Bob. Okay, 1, 2, okay, 3, and here this is 4. Okay, and same way for Bob there are 4 components. Okay, so these are the Alice components 4, and these are the Bob components. Okay, initially 1, 2, 3, 4. Okay, I haven't created any path here yet. Okay, so now see here, first type 3. Okay, so initially let's maintain the count of the edges that I'm going to use. Okay, E. Okay, so initially let's take this. Okay, so type 3 is nothing but for both Alice and Bob, right? So there is one path between 1 and 2. Okay, so initially the parent of 1 is 1. Okay, initially parent of 2 is 2, initially parent of 3 is 3, initially parent of 4 is 4. Okay, same here, parent of 1 is 1, parent of 2 is 2, parent of this 3 is 3, and parent of this 4 is 4. Okay, this is the common thing that we use in this find operation, right? Find and union. Okay, so initially this is like this. Okay, so here see here, 3, 1 to 2. Okay, type 3 means that I need to do for both Alice and Bob. That is my pencil color is blue right now. Okay, so here 1 and 2 I'm going to check. Parents of 1 and 2 both are different. Okay, so now let's join them now. Let's join them. If the parents of both are different, let's join them. Okay, after joining them, let's make 1 as the parent of both. Okay, let's make 1 as the parent of both. Okay, same here. Okay, join this 1 and 2, and let's make 1 as the parent of both. Okay, now my components are decreased to 3, right? Components are decreased to 3. Okay, this is 1 component, this is 2, this is 3. Okay, this is done. So here my components are decreased to 3, and I have used 1 edge. Okay, here my edge count is 1. Okay, then 3, 2, 3. 3 means type 3 for both Alice and Bob I need to do, and for 2 to 3 there is one path. Okay, 2 to 3. Okay, so now let's do one thing. Both the parent of 2 and 3 are different now. Parent of 2 is 1 and parent of 3 is 3 itself. Okay, so parent for both of them are different. So I am going to remove this 3. Okay, and I'm going to remove this 3, and I am going to put this 3 inside this. Okay, and let's make the parent of this 3 as 1 only. Okay, this is done. Okay, so now my components are decreased to 2. My components are decreased to 2 here, and my edge is increased. Okay, so I have used 2 edges. Okay, this is done. Now this is done. Now I reach to type 2. Type 2 means for Bob, and Bob is nothing but green. Okay, type 2 is for Bob, right? Type 2. Okay, so 3 to 4 there is one path. Okay, 3 to 4 there is one path. Okay, so 1 second, let me make sure. Type 2 is for Bob only, right? Type 2 is for Bob only, right? So we are right, and it is green color, right? So see, now 2, 3, 4. Okay, so parent of 2. Now let's see for Bob only. Now 2 means for Bob only. Okay, 2 parent is 1 and 4 parent is 4 itself. Both have different parents. Okay, so now let's remove this 4 and put this 4 here inside this box and make the parent as 1. Okay, parent as 1. So now my component is decreased to 1 here, right? My component is decreased to 1 here, and I have used one more edge, so it is going to be incremented. Okay, 3. So this is done. Now see here, 1, 1, 3. 1, 1, 3. Okay, this. So this 1 is for Alice. So let's make the pencil red. So 1 and 3 both have same parent. I don't need to do anything. Cancel it out. Simple. 1 and 3 both have same parent 1. See here, 1, 2, 4. 2 has parent 1, 4 has parent 4 here. So for Alice, I am going to delete this 4. I am going to add this 4 here. And for now 4's parent is 1 only, and my component is decreased to 1, and I have used one more edge. Okay, 1. Okay, this is done. So now I reach here at this particular edge. Both 1 and 2 have same parent 1. I don't need to do anything. Let's delete this. Okay, so here how many total edges are there? 4. And in the question how many edges given to me? 6. Right, so 6 minus 4 is equal to 2, and 2 is my answer. Okay, So I hope that you guys are clear with this explanation. Okay, so now after this I am going to move to the coding part, and while doing the coding I will explain few more things related to this find, union, and this rank, union by rank, and path compression. Okay, so now let's move to the coding part. So first let's create one class DSU. Okay, so here class DSU. Okay, and inside this we have to create a parent. Okay, so create one parent array, and I am also going to use the rank. Okay, so create one rank array, and also we are using the components. Okay, we are keeping track of the components. Okay, initially there are 4 components, and then okay, so here one more thing. Okay, so if my components both are 1 for Alice and Bob, then that simply means that I have completely traversed my whole graph for both Alice and Bob, and in that case I have to return this output. Okay, otherwise I have to return -1. Okay, so both components should be 1 in the end. Okay, so initially there are total 4 components. Okay, so here let's create the components as well. Okay, components variable private int components. Okay, so now after this let's create one constructor. Okay, public DSU, and let's pass value and n. Okay, so total number of nodes. Okay, initially, so this is going to be total number of components. Okay, so here inside this let's initialize my array. Which array? Parent array and rank array. Okay, so see one more thing here, my nodes are numbered from 1 to 4 now. Okay, 1 to 4. So here I have to write new int n plus 1. Okay, here I have to write n plus 1 because my nodes are from 1 to 4. Okay, 1 to n. And same way for rank, 1 is the parent of 1, 2 is the parent of 1, 2 is the parent of 2, 3 is the parent of 3, 4 is the parent of 4. Okay, we are just doing the initialization first, right? So here just write n plus 1. Okay, then after that we are going to initialize. Okay, but before that components I have already told you we have 4 n components. Okay, initially components are n, and now let's initialize. Okay, let's create every node as its own parent. Okay, so I am going to run one loop int I is equal to 1 and I is less than equal to n, I plus plus, and inside this parent of I is equal to I. Okay, that's it. Okay, this is for my DSU constructor method. Okay, this is done. Okay, so I hope that until now you guys are clear. Okay, so now after that we have to write the find or find method. Okay, so public int find. Okay, and inside this let's say I am finding the x value. Okay, this is what I am finding. Okay, so if my x value is equal to my parent of x, okay, then in that case we have to simply return that x na. Okay, if both have same parent, then simply return x na. Okay, return x. Okay, return x if my x is equal to parent of x. If it is not, then again we have to just return, but we have to, after that again we have to call this method find. Okay, and inside this I am going to pass the value of the parent of x. Okay, this is how we write the find operation. Okay, and just just side by side assign the value of this parent of x is equal to find of parent of x. Okay, that's it. This is done. Okay, this is for find. Now let's move to the union method. Okay, so public void union. Okay, so let's say there are two values, int x, int y. Okay, and here first we are going to find the parents of both x and y now. So int x parent. Okay, how we are going to find the parent? Using simple find method. Find x. How I am going to find the parent of y? So here I am writing int y parent is equal to find of y. Okay, and if both the parents are same na, if the parent of both x and y are same, then we are not doing anything na, then we don't have to perform the union and all. So if x parent is equal to y parent, then we have to simply return. Method is void. Okay, so we are simply doing return. Okay, now after that our rank logic will come. Okay, our rank logic will come after this. Okay, see here. So if this parent's rank is higher, then I have to make this as parent for the union of 1 and 2. Okay, so the person who has higher rank will only become the father. Okay, parent. Let's write further. Okay, so if rank of x parent is equal to rank of y parent. Okay, so if the rank of x parent, okay, x parent is greater than rank of y parent, then definitely who is going to become the parent? Parent is going to be x parent, right? X parent. So here I am writing parent of y parent is equal to x parent. Okay, right? Here after that, else if okay, else if rank of x parent here, okay, let me copy it here. If the rank of x parent is smaller than rank of y parent, then in that case parent of y parent x parent. Okay, so now y parent has higher rank na, so here x parent is equal to y parent. Okay, this is done. Now else part, if both have the same ranks, okay, then we can make anyone as the father, right? If both have same rank initially, then I can make 0 as parent or I can make 1 as parent. Okay, so it's your choice. Okay, so here I am writing just parent of x parent is equal to y parent, and then after that I have to increase the rank of the parent, right? So I am making this as the parent now, so I have to increase his rank. So here I am going to write rank of y parent plus plus. Okay, that's it. Okay, and every time whenever I am doing the union na, I have to reduce the count of this component, which is 4 initially. Okay, component minus minus. So see here, I am doing the union between 1 2 first, then I have to reduce the component count, then I am doing the union of 1 2 3, then I have to reduce the component count. When I am doing the union of 1 2 3 4, then I have to reduce the component count. Okay, so every time I have to reduce the component count. Okay, so this is all for union method. Okay, this is done. Now let's move further. Okay, in this same class, let's define one more method. Okay, in the end we need one component for both allies and both. Okay, so public boolean is single. Okay, so here we have to just return components is equal to 1. Okay, that's it. Okay, that's it that we have to write in the class DSU. Now again go here in our main code. Okay, so here first thing is that I am sorting this edges array based on their type based on their type. Okay, so here I have to write arrays dot sort. I'm sorting edges. Okay, so let's say there are two edges, one is v1 and v2. Okay, these two are parameters, right? v1 and v2 are two edges. Then I have to sort these v1 and v2 based on their index number 0, right? So that is why I'm writing like this: v2 of 0 minus v1 of 0. Okay, this is done. Now after that, let's create the object for both Alice and Bob. Okay, so for Alice I have to create, and for Bob I have to create separately. So DSU Alice is equal to new DSU, here pass n, and same way DSU Bob is equal to new DSU, here type n. Okay, here it should be small now. Okay, this is done. Then we have to count the edges as well these edges one by one. So here I am writing int added edges, and added edge, okay, is equal to 0 initially. Okay, so now let's iterate over all the edges one by one. I am using for each loop. For int edge of this edges array, okay, one by one. So first value is type. Okay, so type value is nothing but edge of 0. Next value is u is nothing but edge of 1, and the next value is v, and v is nothing but edge of 2. Okay, this is done. Here, let me fix this side by side. Okay, this is done. Then after that I am to check if type is equal to 3. Okay, if type is, first we are checking for type 3 now. So if type is equal to 3, then I have to take care of both Alice and Bob, right? So first let's create one boolean, add is equal to false. Okay, initially it is false. Okay, so now here after that, if Alice dot find, okay, I am finding the parent. Okay, if Alice parent is not equal to Alice of find 0 is not equal to Alice of find of v. Okay, first I am checking for Alice Alice dot find of v. Okay, so here simply I am checking the 1 and 2 both have same parent or not same parent. Okay, this is what I am checking for Alice first. Okay, so if both are not same, then I am doing the union, right? Alice dot union u and v. Okay, if I did the union between them, okay, then definitely I have to create, I am adding one edge. Okay, so here I am just making it as true. Okay, so this is just going to check if I have added any edge or not. Okay, so in this case I have added one edge. Okay, same way I have to check for Bob. So let me copy this. There is some issue with the mouse. Okay, so let me write if Bob dot find u is not equal to Bob dot find v. Okay, then I have to do this Bob dot union for u and v. Okay, then in that case also I have to update my add value as true. Okay, so see here, one for this blue color pencil for both Alice and Bob. Okay, so every time whenever I am adding, okay, 1 and 2, I am creating one edge I am adding one only. Okay, if it is for blue so I am adding one only for, okay, because one is used for both Alice and Bob so I am adding only one. Okay, so here if my add is true, if add is true, then simply added h plus plus. Okay, this is done. Okay, so this is done. Now after that, let me decrease some size here. Okay, so if type is 3, okay, so here this type is done. Okay, so here if type is equal to 3, then this is what I need to do. Now in the else part, else if type, okay, let me increase the size now, as if type is equal to 2, if the type is 2, okay, so type 2 simply means I have to do for Bob na. Okay, I have to do for Bob. Okay, so here let me just copy this code. If type is 2, so here I am checking if bob.find u is not equal to bob.find v, then bob.union I have to do. Then here just increase the edge. Okay, so here I am just going to increase the edge instead of using this condition. Okay, because every time whenever I am doing just for bob, I have to increase one edge. Okay, so this is done. Now in the else part simply means that I have to do for this guy Alice. Okay, so let me copy the code for Alice here. Let me copy it and paste it here. And now here every time I am doing just for Alice, then I have to just increase this added edge plus plus. Okay, this is done. Now here, okay, now here let me decrease the size. Okay, so here after this complete for each loop, okay, in the end I am going to check. Okay, let me increase the size now. Okay, so if both the components are same now, if the components are one only for both Alice and this guy Bob, okay, then I have to find the number of removed edges, right? If Alice is single, okay, and Bob is single, okay, we both have single component, okay, then in that case we have to just return edges dot length minus added edge. Okay, this is done. Otherwise simply return -1. That's it. We have written 93 lines of code, right? Return -1. Okay, so now let's run it. Let's hope there are no mistakes. Let's see. Oh shit. So let's resolve the issues now. Line number 38. Let's move to the line number 38. So component I am writing, I think components, let's see, components should be there. Okay, so let's add s here. Okay, let's run it again. So all the test cases has been accepted. Okay, now let's submit it. So see, our solution is accepted, right? And we have completed all the questions for June month, right? So I hope that you guys are able to understand today's problem, right? This question is very big, right? Hard level problem, but it's very interesting topic, right? Related to DSU. Okay, so I hope that you guys are able to understand today's problem. If you guys still have any doubts, then please feel free to ask in comment section. And if you guys want to know more about this find union operation, this union by rank or path compression, then just add a comment. Okay, I will try to explain this in one separate video in a detailed manner. Okay, so meet you guys in the next video. Thank you. Bye bye.